Hey everyone, this is Dr. Brian MacDonald, author of Practical Stress Analysis with Finite Elements, now in its third edition. And today we're going to be doing a plane strain forging analysis of a rectangular block using ANSYS Workbench. So what we're going to do is we're going to do a 2D plane strain analysis of squeezed forging of an annealed copper rectangular block as shown here. So here's our copper block. And we have it placed between an upper die and a lower die. And this is like a cross section, a two-dimensional cross section through it. So with the plane strain assumption, we're assuming that the block is quite thick coming out of the page. Okay, so if you remember, plane strain assumes that we have zero strain coming out of the page. So we can have stresses coming out of the page, but we'll have no strain. So the block is very long in the direction coming out of the page. So the copper block is then placed between two steel dies, and a pressure load is applied to the upper die to compress the copper block and cause permanent deformation. So our lower die is fixed here, so it's on a very solid bed, and the top die here has got a forming pressure applied to push it down and to squeeze this block in between the upper die and the lower die. So in this case, the objective of this analysis really is to determine the forging pressure required to reduce the height of the bar by 25%. We're told that the bar has a square cross section and has a height here of 0.1 meters and a width of 0.1 meters as well. So again, just to emphasize that this case study with all the details we're going to use is from the book, and it's again from the third edition of the book, and it's on page 400 of the book. So we're looking at case study H, which is on page 400 of the book. So the first thing we're told in the case study is that experimental tests on the annealed copper materials showed that we had a Young's modulus of 110 gigapascals, a Poisson's ratio of 0.34, a yield stress of 33 megapascals, and a failure strain of 0.6 megapascal. Sorry, 0.6. There's no units in strain. So we'll assume that the dies then are made from tool steel and they do not deform significantly during the forging process. So we can use a linear elastic material model for steel for them. But we will have to use a plastic model for the block because the block is going to permanently deform. So, as I've just mentioned, the block is going to permanently deform. So this is a non-linear problem. We are using a non-linear material for the copper. We're also going to have to put contact between the dies and the copper block because the dies are touching at the copper block and the forging pressure has been transferred through the die into the block. So we'll have contact regions here and here. So in order then to kind of get an idea of what kind of result we should be doing and to validate our finite element model, we're going to use plane strain forging theory. So again, this is shown in detail in the book. We'll just quickly hop over there just to show you what that looks like. So here we are in the book, we're on page 400. You can see the definition of the problem, case study H, there, section 11.1.9. We're given all our assumptions here, which I'm kind of going to talk through as we go through them. And we have this analytical theory here, and we end up, after doing the analytical theory, with a table which shows us some results that we can try and validate our model against. So let's just go back to the presentation then. So we're going to use plane strain forging theory. So if we assume that the initial yield stress, which is Y0, is equal to the uniaxial yield strength for the material sigma Y. So sigma y is the yield strength we get from our tensile test here. So these are our tensile test results or compression test results, whichever. Okay, so here we're going to say that y0 is a sigma y, which is 33 megapascals. So the resultant yield stress due to any deformation y1 then is going to be given by y1 is equal to y0 plus the tangent modulus times the strain that is at that deformation level. So strain then is obtained from the height before, which is h0, and after deformation, h1. So strain is the natural log of h0 divided by h1. So again, this is true strain, okay, not engineering strain. Moving on from there then, the tangent modulus can be calculated then. So again, the tangent modulus, maybe we'll just briefly take a quick look at what that is. So I've just gone back in the book onto chapter 6, which is the chapter on material models, and I'm on page 212. And we'll just zoom in a little bit here on this figure. So if this is our stress strain graph here, so you can see we have a dotted line, which is our stress strain graph that we get from a material test, be it a tensile test, whatever. The easiest way we have of modeling that is using a bilinear model. So we have one line for our elastic region, which is given, the slope of this is given by Young's modulus, and then we're going to assume that this curved portion here also has another line. So clearly it doesn't, but it's just a very, very simple assumption. And we're basically, that line makes a tangent to the curve that the actual stress strain curve takes. So the plastic portion of the curve here. So a lot of the time we don't have a lot of information about the various points in this curve, so we can't reconstruct this curve. But from a book of tables, you can normally find things like the failure strain, and you can normally find the yield stress. Okay, and sometimes you'll find the ultimate tensile stress as well. So if you know the ultimate tensile stress, if you know the yield stress, and you know the failure strain, which is, here I've drawn the failure strain a little bit further out than it actually is. It should be back here somewhere. It's normally quite close to the ultimate tensile stress. So you essentially can find the slope of this line because you know the yield stress. We know that yield normally occurs at the proof strain, which we normally designate as 0.2% strain. We know the ultimate tensile stress, and we will assume that that point is the failure strain. So in other words, we have the x and y coordinate of both of those, and we can work out the slope between those 2 points. And that's the tangent modulus, or that's an estimate of the tangent modulus. Okay, so just going back to our presentation again. So here, that's the equation I just gave you there. It says the tangent modulus is the ultimate tensile strength minus the yield strength divided by the failure strain minus the proof strain. Okay, so we can work it out from that. And if you put those values in for our copper, you end up getting 167 megapascals. And again, where they come from, again, go back to the book and look at that. But I think here you're given some of the values. You're given E, you're given 33, and there's more values in the book. Okay, so for the moment you can just assume the tangent modulus is 167. The pressure then required to cause the reduction in height of a block of width b from h0 to h1 according to plane strain theory is going to be this here. So it's going to be y1, which again, y1 is the resultant yield stress, times e to the power of mu b divided by h1, where mu is the coefficient of friction between the forging dies and the bar. So using the above equations, then in this case we can calculate the following. So first of all, y0 is 33. Our original height is 0.1. We're trying to reduce this height of the block by 25%. So our subsequent height would be 0.075. This is meters. So the strain from getting to there is going to be 0.287. So it's about 28% strain. Our tangent modulus then is going to be 167 megapascals, and y1 is going to be 81.04 megapascals. So we can look at two different conditions. We could look at zero friction, and we can look at 0.05 friction, which is a good estimate of friction between lubricated metals. We're going to just concentrate on this one today. Okay, so we're going to say the friction is equal to 0.05. The height, the width of the block is 0.1, and that's saying to us that we should need a forging pressure of 86.62 megapascals to get our 25% reduction in height. Okay, so what are we going to do today then? We're going to build a plane strain model of this, which is going to look like this. So we're going to use symmetry and just model one half of it. Okay, so we can't model 1/4 because the loading is not symmetric. Okay, so the top one has got a pressure, the bottom one is held. Okay, so the loading is not symmetric here, but it is symmetric this way. So we can just model 1/2, and our model is going to look something like this at the end of the day. Okay, so let's just go over to Workbench and start working our way through that. Okay, so I have Workbench set up, and I've given my project plane strain forging as a name. and I'm going to do a static structural analysis. So in this case, it's going to be a non-linear static analysis. Still static. We're still going to assume that loads are applied so slowly they don't cause any vibration effects. But we're going to have non-linear materials, and we're going to have non-linear boundary conditions because we're going to have contact. So again, I just drag my static structure over here. And as usual, the first thing I'm going to go in is and change my engineering data. And what I want to do is I want to create two materials. So I'm just going to click die steel, and I'm going to put another one and call it annealed copper. So I'm going to start off with the die steel. That's an easy one. So I'm just going to double click on isotropic elasticity. And I was asked to, if we go to the book, again, just quickly, let's just jump in here, and it tells us, well, the tool steel for the dies has 210 by 10 to the power 9 pascals, and Poisson's ratio is 0.27. So let's just put those values in there. So I have 210 e to the 9 pascals, and I have 0.27. So that's my steel defined. Now I want to click on the copper, and I'm going to need isotropic elasticity first, and then I'm going to need a bilinear-isotropic hardening. Okay, so remember, the bilinear is this second line we have that is modeling the curved portion of the stress strain curve. It's where the tangent modulus is calculated. Okay, so I double click on that as well. So the first thing I have to do is put in the isotropic linear elastic properties. So I'm going to click on Young's modulus, and then let's take a quick look at the book. In this case, we're looking for 110 gigapascals and 0.34 Poisson's ratio. So 110 e to the 9 and 0.34. And then for the bilinear, it's asking us for two things. It's asking us for the yield strength and the tangent modulus. So let's just see what we have here. We have 33 megapascals and 167 megapascals. So it's very important that, generally speaking, for metals, your Young's modulus would be in gigapascals, your stiffness, but your yield stress, ultimate tensile stress, and tangent modulus will generally be in megapascals. Okay, so not in all cases, but generally. So it's an order of magnitude lower. Okay, so 33 megapascals. It'd be very important. It's e to the 6, not e to the 9. Okay, so let's just jump back to Workbench again. So we have 33 e to the 6 in there. And again, just a quick check, 167 e to the 6. 167 e to the 6 in there. So here we entered 110 gigapascals, which was 110 e to the 9, and here we had 33 e to the 6 and 167 e to the 6. Okay, if I want to take a look at the curves here, so there's my isotropic elasticity. Okay, it doesn't really show me anything, it just shows me a point. If I click on my bilinear isotropic hardening, you can see here it's showing me the elastic part of the curve and the plastic part of the curve. And you'll see that the plastic part is almost flat. Okay, and that's kind of what I'd expect. Okay, because the elastic portion is much steeper. Okay, so remember that. So that's gigapascals and this is megapascals. Okay, so I should see it looking almost flat. There is a slight curve to it. It can't be really seen in this figure, but it shouldn't be as a high an angle as the elastic portion should be. Okay, so that's my engineering data done. So I'm just going to go back to my project. Again, always a good time just to have a little save. And now I'm going to start my geometry, and I'm going to go new design modeler geometry, and I'm just going to wait for that to open up. Okay, so here I am in my design modeler, and I'm going to start off by sketching on the XY plane. So I click on XY plane. I'm going to click up here to look at the plane, and I'm going to click on sketching. First thing I'm going to do is check my units. I'm in the meter and degree, so that's perfect. That's what I want. In sketching then, normally just a good idea to put on a grid just to make sure you're not drawing something that's completely off the wall according to the dimensions you're looking at. So if you remember, our block was about 0.1 meters, so I'm going to make the grid 0.05, which is about half the width of our block. Okay, and what I can do then is just zoom in there. So you can see at the moment my ruler is showing I'm at 30 meters, is that much, so I'm obviously way too far out. So let's just zoom right in until we see that grid turn up. Okay, so there we are. So I'm going to start off by drawing the block. Again, let's just take a look at our schematic of what. So here's my problem, and here's what my model is going to look like. So remember, my block is 0.1 meters by 0.1 meters. So I'm going to want a block here. The gray block is going to be 0.05 meters across by 0.1 meter high. Okay, so let's just go back to our design modeler and do that. So I'm going to say I want a rectangle, and I'm going to go down here and pull it up to there. Okay, and then just to check, it's always a good idea just to put dimensions on it as a check. So a vertical dimension, I'm going to say I just want to put points. I click here, here, and pull out my dimension, and it's 0.1 meters. Perfect. Now I'll do a horizontal one up here just to be sure. Oop. And pull that up, and it is 0.05. That's perfect. Okay, so now that's my block. I can go back to modeling. Just expand on XY. There you can see I've got sketch 1. So now I'm going to go to concept, surfaces from sketches. Here it's asking me, well, which objects do you want? I'm going to click on sketch 1, go OK, and I'm going to add material is fine for this one. I'm going to go generate. So now I have one surface body drawn there for my block. Okay, so now we need to repeat that process and create the blocks. So what we're going to do is click on the XY plane again, and we're going to go up here to the button for new sketch. So it's almost like the sketch outline with a little star in it. So we've got new sketch, so we've got sketch number 2, so we can click on that, go back to sketching, and again we want a rectangle, and we want this one coming across up here, and again maybe just go out twice the width of the block, and the height doesn't particularly matter. Let's just go with that. So again, in just always a good idea is to do the dimension, maybe in case we need it later, we need to change something or we want to get some data. So again, we're just looking, in this case our dimension is 0.1 meters. Okay, and we won't bother doing the height. So we're going to go back to modeling again, and now we want to go concept and create surface from sketches again, and this time we want sketch 2. We want to go apply. Very important this time, change add material to add frozen, because we don't want it to join it on to the existing block. If we had add material, it would just join it on to what's there and it would become that shape there. Okay, we want them to be two separate surface bodies. So once we've add frozen there, we can go generate, and you can see it's given it a different color. Same thing once more, click on the XY plane, click on new sketch, sketch 3 this time, and again let's go into sketching, and we want a rectangle, and again exactly the same thing. There we go, there's our block. Back to modeling, concept, surface from sketches, click sketch number 3, make sure to change it to add frozen, and generate. And that's it done for our geometric model. Okay, so that's all we need to do here. We'll just do a save on that. We can close down our design modeler. Okay, so before we actually go and open up our finite element model, then we just need to make sure that we tell it that we're going to actually be using a two-dimensional geometry. So click on geometry, and we change the analysis type to 2D here. And once we've that done, we can double click on our model, and we'll just wait for the modeler to open. Okay, so our finite element modeler is opened now, and we can see we have our geometry here. So the first thing I want to do is click on geometry, and let's just give the parts names so we know what we're dealing with. So the first surface body there, let's just rename that and call it the block. Okay, so our copper block, whatever we want. And the next one is the upper die, so let's just call it that. Again, it doesn't really matter what you call these, it's just for your own convenience. And the outer one is the lower die. Okay, the next thing we need to do is make sure the right materials are put on those. So back to the copper block, we want to make sure that that is the annealed copper, and that the upper die is the die steel, and the lower die is also the die steel. So the structural steel is the default that comes with Workbench. Okay, so we just change it to the ones that we defined. So moving down here then, the next thing what we want to do is put in a symmetry boundary condition. So we want to tell it that this edge here is symmetric. So we click on Model, right click on Model, and insert symmetry. So symmetry comes there, and then click on right click and insert symmetry region. It's asking me what geometry do I want. So it's fixed on, let's fix it on an edge. Okay, and I'm going to pick that edge, hold down the control button, that edge, and also that edge. And then in here I go apply, and it says where is the symmetry normal. So it's on the x-axis. Okay, that's the one we wanted symmetric. So there's our symmetry region defined. Next thing we want to go is look at our contact. So one of the great things about Workbench is it actually works out the contact for you in advance. It finds regions that are touching, and it has a guess as to what's going on with the contact. So if we expand out the connections, you will see that we've got contacts. Let's expand that, and we have two contact regions. So here there's contact between the copper block and the upper die, and contact region 2 is between the copper block and the lower die. So let's just take a look at both of those. So unfortunately, Workbench has guessed that they're bonded, so that's not what we want. So Workbench is basically guessing that those two are glued together and they can't move. So it's clearly not what we want here. So we click on bonded, and then we can see we have several different types of contact. So in this case, it's a frictional contact. Okay, so remember, we're going to do the frictional version of the analysis. Again, let's just quickly jump back to our problem overview, and remember we had two friction levels, so we're going to look at the 0.05 friction level. And what that means is if you have friction between the block and the die, when the block expands out, you'll get this barreling effect, okay, because the bottom surface of the block can't move over to the right as much as it wants, whereas the middle of the block can, so you get the barreling effect due to friction. Okay, so that's what we're looking for in our analysis. Okay, so let's just go back to our problem again. So we had a friction of 0.05. Okay, so frictional, and we need to change that. So you can see that the copper block to upper die has changed to frictional. And again, we're going to do the same thing here between these two. And here it shows you the line. So just interesting to note, in the side windows here, you can see that the contact body is in red. So there's a red here, and the target is in blue. So again, if you think about, we're pushing down here, so it's identified them correctly as the contact and the target. Again, change that from bonded to frictional, and put in 0.05 for the friction coefficient. Okay, so that's our contact sorted out. Okay. So the next thing then, if we work our way down the project tree or the model tree, is the mesh. Okay, so we need to put a mesh in. So if I just again do the default mesh, it's probably going to give me something that's not great. Again, you know, that's not great. If you think about what's happening in this model, this gray block here is going to have to significantly deform, okay? And it's only giving me about 7 or 8 elements across, and maybe about 14, 15 up, okay? So that's really not enough. The other thing too is that in terms of contact, the way contact works is it essentially makes artificial springs in between these elements, and it makes them between nodes. So if you look at these nodes, they're not joining up with each other either. Okay, there's probably mid-side nodes there, maybe they're joining up with those. But it'd be nicer if we had a much more regular mesh here. So what I'm going to do is just go in here, First of all, I'm going to select that I want quadratic elements. So that's elements with mid-side nodes and they can have curved edges. Okay, so when this is deforming, it's going to be, it's going to get quite curved. So, it's important that I'm able to model that correctly. The other thing too is I'm not just going to accept what it tells me there. I'm going to give it a specific element size, and I'm going to go down to 10025. Okay, just as a starting point anyway. Let's see how we get on with that. So again, let's just update the mesh. Okay, so that's a reasonable enough mesh, very regular. Elements are all lining up with each other. You could argue that we don't have to have the dies meshed that finely, and that we probably should have the block meshed more finely. But let's just go with this for the time being. Okay, so moving on down then, go to our static structural, and we have to change a couple of things in the analysis settings here. So if we click on analysis settings, so the first thing we have to do is here we have this large deflection option here. So if you remember, a normal linear static analysis only works inside in the elastic region, and we're below the yield stress, and we're not getting very much deformation. So the yield stress normally corresponds to a strain of 0.2%, which is very small. So here clearly we're going to be straining to 25%. So we have 25% reduction in height. So we need to tell the program that we're looking for a large deflection, that we're not dealing with the small deflection type analysis. So what we need to do is go in here to large deflection and turn that on. And that will allow the analysis to run a different type of solution where it knows that large deflections are okay, and it will take on the plasticity parameters. So normally when I'm doing a metal forming analysis and I have lots of contact and large deflection, I would mess around here with the number of sub-steps and load steps as well. What I'm going to do is I'm going to let it do it in one step, but I'm going to say automatic time stepping is program controlled. So if it wants to break down the number of sub-steps to solve this, it will do it, and it is going to do it here, because it's not a good idea to solve something like this in one step. So we'll maybe talk about this in a future tutorial when we get into more complex control of solution and talking about nonlinear solutions. But for the moment, just make sure automatic time stepping is program controlled, and maybe leave everything as it is, and we'll see how we get on with that. Okay, so main thing here was to turn large deflection on. Okay, so now we need to put some loads and boundary conditions. So what we're going to do as a first step is we're going to apply a displacement to the top die. We're going to move the die down by the amount that we want, and we're going to see what the reaction force as a result of that is, which tells us the force that's required to reduce it by 25%. Later on then we'll go and put in the pressure load and see if they work out. That's in the book. Okay, so we're going to go to static structural, we're going to go insert, and we're going to go down to remote displacement here. Okay, so it's a remote displacement, and we're going to apply it onto the top die. So the first thing it says is, what geometry do you want? So we want that line there. Let me go OK. And then it's saying to me, well, what do you want to do with X, Y, and Z? X, I don't want to move, so I want that to stay constant. I don't want any rotations either, so I'm going to say that constant. And the Y component, I want to move down by 25%, which is minus 0.025. Okay, so that's my load on the top die, or actually it's a constraint really. It's a fixed displacement, and I'm going to put a similar one on the bottom die. So again, I'm going to go insert remote displacement, and I'm going to pick the bottom surface here and go apply. And in this case, I'm going to put all of them as a constant, which means they'll all be set to 0. So we'll have no movement of that bottom die. Okay, so the next thing then is I'm going to maybe tell it what kind of results I want. So I'm going to insert a deformation, and I'm going to be very interested in the deformation in the Y direction, obviously. Oh, sorry, I didn't mean to do that. I meant to do a directional one. Just get rid of that. So I'm going to go click on Solution, Insert Deformation Directional, and I want it in the Y-axis. Um, Also good to look at things like strain and stress in the wider axis as well. So let's just look at normal strain in the y-axis, and maybe stress again in the y-axis, and then y-axis not Z, and then one more which is von Mises stress. So von Mises stress is a yield criteria. It's also very good. It's an equivalent stress, so it's very good at looking at average stress in problems like this where you've got nonlinear material behavior, so plasticity. Okay, so I think we're ready to go. So let's just issue a solve command. So it should just take a few minutes to solve. You might get a warning down there, but it should be okay. Again, if you're interested in what's going on in the solution, you can click on solution here and solution information. So this is just going to give you a log of what's going on, so you can see there's convergence going on in the background and it's trying to converge the model. Solver output, you can get a graphical indication of that by looking at force convergence. So again, we'll maybe talk about this in a future tutorial, but essentially you can see that when a substep is converged, you have the force convergence, the force criteria go together. So there you see the green dash means the substep has been converged. Okay, so you see when that happens whenever these two graphs overlap or go together, if you like. And the orange one is telling you when a bisection occurs. That means when the solver is finding it quite difficult to actually solve a particular substep or an increment of loading, and it basically bisects it, in other words, divides it in half. So what's going on here is that the solver isn't applying the full load in one step and trying to solve this. It's breaking it up into sub-steps and trying to solve it bit by bit and then putting them all together. That's a very, very simplistic analysis of it. As I said, we'll talk about it maybe in a future tutorial. There's a lot of information on this in the book in chapter 8 when it talks about nonlinear solution methods. So we'll just wait for this to solve. So what I'm going to do now, rather than waste YouTube time, is maybe just pause my recording and we'll just come back to it when it's solved. Okay, so that's just solved for me. That took about 10 minutes on my computer. You can see there that it had 2,451 iterations, so it had 2,451 guesses in order to solve that. So let's see what it came up with. So first of all, the directional deformation. So as we expect, we're getting the blue area here is the most amount of deformation, which is 0.025, which is basically what we told it to do. If we look at our strain, then we can see the different values we have for strain. Again, you know, we're dealing with compressive strain here, so the block has strained the most, obviously, so we have quite little strain out here. Again, normal stress here, not such a good picture this time. It's hard to see the stress in the block because of the stresses in the dies. And equivalent stress, again, showing us the kind of average stress or von Mises stress. So again, the highest stress there occurring at the contact region. So you can see due to the friction that we have the barreling effect going on there. So important thing to notice up there is that, you know, Workbench straight away has auto scaled it. So I'm just going to put it down to the true scale. Okay, so you can see there, if we just go to our directional deformation, okay, and maybe a good idea just to see if we can show the original shape. So let's just say I'll show undeformed wireframe. So there's our original shape and there's our new shape. So you can see the barreling effect is there. It's not as pronounced as Workbench showed it to us as first. So that's the true scale on. So the black oblong is the original shape, so you can see it's reduced its height and it's also barreled out. Okay, so just put on the elements again, and again just looking at equivalent stress. Okay, so a more useful result here would be to get the reaction force. So we've forced the top die to move down a bit. Now let's see, well, what reaction force did that cause? Okay, so again, I'm going to go into solution. I'm going to go insert, and in this case, I'm going to go probe, and I want a force reaction. And it says to me, what boundary condition do you want to check that at? So let's do it at both of them. So remote displacement, this is one there. Let's put another one in at the other one just for the laugh. Again, another probe, force reaction. Put that at remote displacement too. So we need to evaluate those. So we just go right click on solution and go evaluate all results. Okay, so we have our force reaction there. And we'll have to move down through the sub-steps. So you can see the solution here. We got about 181 sub-steps. So we got 5.5802. Okay, and straight away I know that's wrong, and straight away I know, or just remember that I forgot to do something. So what did I forget to do? If I go back up here to model, geometry, I've set it at plane stress. Okay, so we need to rerun that analysis, and we need to do it at plane strain. Okay, so silly mistake, plane strain. So you can see that everything else is okay, but I now need to do another solution. So I'm just going to tell it to solve for plane strain. And it shouldn't take as long because it has a lot of the calculations done. So again, I'm just going to pause it and wait for it to solve. Okay, so now my plane strain analysis has solved. So again, the results should be a bit better this time. So again, there's my 25% reduction as I'd expect. Again, it's going to show the undeformed wireframe, so I can see that the original shape and the new shape I have. Again, that's looking, contours are looking a bit better there, more like what you'd expect. And we should see if we look at, yeah, exactly. So I was a bit puzzled the last time I was looking at the values for stress and strain, wondering why I didn't get this kind of shape in here, because that's kind of a characteristic shape that you obtain in this analysis for stress and strain results. So here's my equivalent stress. My strain in the y direction, and now I'm going to look at the reaction forces. So in this case, the reaction force is 7.2 e to the 6 newtons. Okay, now if I check the other one, it's 7.2 e to the 6 newtons as well. So if you remember the analysis from the book, let's just hop back there for a second. So in the book, it was telling us that we should be getting a pressure of 86 megapascals. Okay, so pressure is force over area. So if you took a force of 8.6 divided by 0.1, okay, so the area is effectively going to be a line here because we're talking about a unit thickness. So 0.1 by 1. So divide what the result that we got here, the 72 by 0.1, that would, or 7.2, sorry, by 0.1, that would give us 72 megapascals. Okay, so we're a bit out. Okay, according to what the book is saying. So again, here, same thing there, 72. So what we're going to do now is we're going to just go back and we're going to apply the pressure load and see what happens. Okay, so we're going to suppress one of the displacements. So with this one, the remote displacement there, so we're going to go back in and we're going to suppress that. Okay, so that's out of the equation right now. So now we're going to go ahead and put in a pressure load. So we're going to go insert pressure, and we're going to put it on that line there. Go apply, and we're going to define the pressure in terms of components. So the x component is 0, and the y component is going to be, again, if we flip back over to the book, 86 megapascals. So it's going to be minus 86 e to the 6. Okay, and you can see that we have that pressure going the right direction there. Okay, so now we can Just do a save command and we just do a solve on that. So before I issue the solve, you have to suppress the reaction force at the top. Okay, so I was getting a problem there for a second where I forgot to suppress that reaction force. So you can either delete or suppress them. No harm, get rid of both of them and wait for it to solve and then put them back in again. Okay, so again, I'm just going to pause it while it solves there. Okay, so I've got my solution here, and again, the reaction force here, I'm just going to delete that. I suppressed it to get it to solve. Just delete it. We don't need it anymore. I still have reaction force at the bottom here. Let's just take a look at everything again. So here is my directional deformation. So you can see here that the die is deformed a little bit here. There's a little bit of a bent over of the die due to the pressure load rather than the remote displacement. So the remote displacement is a little bit better from that perspective. Again, always a good idea just to show the undeformed edge, just to make sure I'm getting what I want, just making sure my scale is set to true scale as well. Let's go back to showing elements. Again, my elastic strain, normal stress, slightly different values here, but again, maybe a bit difficult to see, still getting that kind of cross shape that I got the last time. I'm getting a lot more stress up here now because I've applied a pressure load to it. So because it's not a remote displacement, it's not moving it as a rigid body like it was before. But if I look at my reaction force again, I'm getting 8.847. Again, remember I applied a 8.6. Okay. Again, let's just check our displacement. So I'm getting 29 millimeters here. Okay, so again, I'm not tying up too closely to the book. So in the book, we applied 86.62 and that gave the 25% reduction. So I'm getting a bit higher with that here, okay, than was obtained in the book. Again, the friction results for the book, again, you can see that the barreling effect going there. So even in the book, the FEA was 88 and the analytical was 86. So, I'm a bit different again. I could probably definitely remesh my model and hopefully get a bit better. Distribution of ANSYS strain in the model. Again, I can try and compare my results to that. So I'm getting about 48% strain, maximum strain. Again, let's just take a look at we haven't got von Mises strain. Let's pull up von Mises strain. Just evaluate that. Again, hard to see it without the dies are actually overwhelming the results, if you like, here. So again, not getting those kind of values. Let's just have a look at the book again. 48%, no. If you're not getting that, I'm getting 38%. Okay, so there is some differences here. I think by remeshing we probably could get a bit closer to the book. I think a little bit conscious of how long this video has become. We're a good bit into this now, so I think maybe we'll leave that as an exercise for the time being to maybe go back and remesh. So again, come back to here, maybe look at that value there, change that value, bring it down, particularly in the block. Bring it down a bit lower and see if you can get closer to the results in the book. So just leave that bit as an exercise. I think really what we've done here in this video is we've shown you how to do it. We've shown you how to set up the analysis. Remember the mistake we made at the start. We ran our initial analysis and forgot to change that one to plane strain. So again, that should have been my first step in geometry. Change that to plane strain. So again, just maybe the salient points here. Change that to plane strain. Make sure you set your materials here on 3 different bodies. Make sure you set your symmetry region. Your contact, make sure you change the contact, which will come in as automatically being bonded. Make sure you change it to frictional and put in your friction coefficient. Your mesh, then make sure you get a fairly fine mesh in your block in particular. And then your analysis settings, again, the key point, turning on large deflection. If you're having difficulty getting your analysis to solve, you may need to change this number of steps and sub-steps. Leaving it at program control worked out for us in this case. If you want to find out the force required to get 25% reduction, use the remote displacements. We did it that way, and then we went back the other way and put in a pressure load and found the force that way as well. Okay, and you can do that by putting in reaction forces in here. Okay, so again, to do that, it's insert probe and force reaction. So there's quite a bit in that tutorial that we did today. We have used nonlinear materials. We have used contact. We've used a friction model. So it's quite a bit in there today. So again, remember, all of this and everything I've talked about is covered in much more detail in the book. So everything is a chapter in the book on material models which discusses using the nonlinear materials. There's also a lot about contact in the book as well. So this tutorial took in a lot of things today. So we took in plane strain analysis, we took in using contact for the first time, and we also took in using nonlinear materials. Okay, so let's just stop there for this one, and we'll see you at the next one.